Welcome students to the lecture number 2 of Computer System Architecture. My name is Raju Sharma. I'm working as Assistant Professor Computer Application in Siddharth Government College, Nadaun. Students, in this lecture we will discuss a very important topic of digital electronics and computer system architecture, Boolean algebra. Firstly, let's understand what is Boolean algebra. Boolean algebra was introduced by the mathematician George Boole in year 1847. Boolean algebra is the branch of algebra which deals with Boolean or binary variables. We know that the binary or Boolean variables are those variables which can accept only two values, true or false, which are also represented by 1 and 0 respectively. Students, it's important to understand that computer can understand binary language only. Therefore, it is very important to understand the basic concepts of Boolean algebra. Now, let's understand what is the use of Boolean algebra in computer architecture. Students, we know that the computer processes data in binary form only. It means that all the instructions we give to the computer are ultimately changed to the binary form. Also, all the computer hardware components such as gates, circuits, etc., they work on binary data only. So we need a theoretical system which can relate us to the computer hardware. Boolean algebra play this role. So the uses of Boolean algebra in computer architecture are: Boolean algebra represents the algebraic relationship between the variables given in the truth table. Secondly, it represents the relationship between the input and output of the logic circuits. Third one is it helps the hardware designers to build simpler circuits with the same functionality. Now, let's understand some basic rules or identities given in the Boolean algebra. In this slide, I have taken the identities which include and or operation only. We will understand these identities one by one. The first identity is a and 0 is equal to 0. It means that when we apply the AND operation between any variable and 0, we will always get 0 in the result. We can verify this identity from the AND truth table also. Here we can see whatever the value of A, if the value of B is 0, then the output is 0. This identity is known as dominant law. The second identity is A and 1 is equal to A. It means that when we apply AND operation between any binary variable with 1, we will get the same variable in the result. We can also verify this from the truth table of AND. It shows that whatever the value of A, if the value of B is 1, then the result will be same as the value of A. This rule is known as identity law. The third identity is A and A is equal to A. It means when we apply AND operation on any Boolean variable with itself, we will get the same value in the result. For example, 0 and 0 is equal to 0. Also, 1 and 1 is equal to 1. This rule is known as idempotent law. The fourth identity is A and A complement is equal to 0. It means if we apply the AND operation on any variable with its complement, then we will get 0 in the result. For example, 1 and 0 is equal to 0 and 0 and 1 is also equal to 0. This law is known as the complement law. The fifth law is the commutative law. It says that A and B is equal to B and A, which means on changing the order of the variables, the result do not get affected. For example, the result of 1 and 0 and 0 and 1 is same. The sixth law is the associative law. It says that when we have more than two variables, then the sequence of applying of AND operation do not affect the result. For example, when we have three variables, say A, B and C, and we want to apply AND operation on them, then when we apply if we apply AND operation on A and B first and then on C, then the result will be the same when we will apply AND operation on B and C first and then on A. The rule number 7 to 12 are related to the OR operations. Rule number 7 says that when we apply OR operation on any Boolean variable with 0, then we will get the value of same variable in the result. For example, 1 or 0 is equal to 1. Also, 0 or 0 is equal to 0. This rule is known as the dominant law. Rule number 8 says that when we apply OR operation between any Boolean variable and 1, we will get 1 in the result. For example, 0 or 1 is equal to 1 and 1 or 1 is also equal to 1. Rule number 9 says that A or A is equal to A, which means when we apply the OR operation on any Boolean variable with itself, we will get the same Boolean variable in the result. For example, 0 or 0 is equal to 0 and 1 or 1 is also equal to 1. The next rule says that A or A complement is equal to 1, which means that when we apply Boolean OR operation on any Boolean variable and its complement, then the result will be 1 always. For example, 0 or 1 is equal to 1 and 1 or 0 is also equal to 1. Rule number 11 says that A or B is always equal to B or A. It means that on changing the order of the variable, the result of the expression do not change. For example, 0 or 1 is equal to 1 or 0. Rule number 12 says that if we have more than two variables and we want to apply OR operations on them, then the sequence on which we apply OR operation on them do not affect the result. For example, if we want to apply OR operation on A, B and C, then we can apply OR operation on A and B first, or we can also apply the OR operation on B and C first. The result will not be gets affected. Now we will discuss few more Boolean algebra identities. First one is A bar A is equal to A. It means if we apply the complement operator twice on any Boolean variable, we will get the same Boolean variable in the result. For example, 0 bar 0 is equal to 0 and 1 bar 1 is equal to 1. The identity number 14 and 15 are known as the distributive laws. According to identity number 14, A and B or C is equal to A and B or A and C. Here we can see that the AND operation is distributed on both the variables which are combined with the OR operator. The identity number 15 says that A or BC is equal to A or B and A or C. Here we can say that the OR operator is distributed on the variables which are combined with the AND operator. Rule number 16 and 17 are known as DeMorgan laws. According to rule number 16, A or B complement is equal to A complement and B complement. Similarly, the identity number 17 says A and B complement is equal to A complement or B complement. DeMorgan laws or theorem play a very important role when we deal with NAND and NOR gates. DeMorgan theorem says that a NOR gate function A or B complement is equivalent to the function A complement and B complement. It means we can construct a NOR gate through OR invert and invert AND. So we have two separate symbols for the NOR gate. Similarly, the NAND gate function A and B complement is equivalent to the A complement or B complement. It means to construct a NAND gate, we can use AND invert and invert OR. We have separate symbols to represent these NAND gates. Now, let's discuss some examples where we will use Boolean algebra to simplify the Boolean expressions. In this example, we want to simplify the expression A and B and C, or A and B C complement, or A complement C. Here we can say that the term AB is common in the first two terms, so we can take it common and the expression will become like this: AB bracket C plus C complement bracket close plus A complement. Now we know that C plus C bar is equal to 1 from the properties. So the next line, the expression will become AB and 1 plus A bar C. We also know from the properties that if we apply AND operation with any variable and 1, we will get the same variable. So AB and 1 is equal to AB. So after the simplification of the function, we will get the function AB or A bar C. Now let's look at the circuit diagram of these functions. Figure A is the circuit diagram of the initial function, and here you can see that we have used 3 AND gates, 1 OR gate and 2 NOT gates for the construction of this function. And the figure B is the circuit diagram of the simplified function, and here we have used only 4 gates, which are 2 AND gates, 1 OR gate and 1 NOT gate. So we can simplify. So in this way we can simplify a circuit, a complex circuit, to a much simpler circuit. Now let's take another example. Here firstly we will apply the distributive AND operation, and the result of this will be A bar or B bracket start A bar B plus A bar A. Now we know that A bar A is equal to 0, so now the expression will become A bar B bracket A bar B or 0. Now from the Boolean algebra properties, we know that OR operation between any Boolean expression and 0 will result in that expression itself. So now the expression will become A bar or B bracket close, both the bracket close, A bar B. Now we will distribute the OR operator on A bar B. So now the expression will become A bar B or B A bar B. We also know that A bar it can be written as A bar, and B it can be written as B. So now the expression will become A bar B plus A bar B. Now from the properties we know that on applying the OR operation on the same variable, we will get the same variable in the result. So the final output or the final simplified expression is A bar B. Now let's take another example. A B bar C plus BD plus A bar B bar C. Now firstly we will distribute A B bar on C plus BD. So now the expression will become A B bar C plus A B bar B D plus A bar B bar bracket close C. Now we know that B bar B is equal to 0. So now the expression will become A B bar C plus A0D plus A bar B bar C. We also know that if we apply AND operation on variables, if one of them is 0, then the result will be 0. So now the expression will become A B bar C plus 0 plus A bar B bar C. We also know that if we apply OR operation on variables and if one of them is 0, then the result will be the variables except 0. So now the result will become A B bar C plus A bar B bar bracket close C. Now in the next line we will distribute the A B bar C plus A bar B bar on the variable C. The expression will become A B bar C C or A bar B bar C. Now we know that C and C is equal to C. So now the expression will become A B bar C plus A bar B bar C. Now we can take B bar C common. So the expression will become B bar C bracket A plus A bar. Now we know that A plus A bar is equal to 1. So now the expression will be B bar C1 and which will finally will result to B bar C. Students, these are a few questions for the practice purpose as an assignment. Please submit the solution of these questions within 3 days. This is the end of lecture number 2. Thank you very much for attending this lecture. See you in the next lecture.